it. Yeah. Thank you very much. I would have just completely forgotten this. Just 1 minute, and then we should be able to start. Meanwhile, what should I say? Okay, I think it is recording. What's happened here? So is everything okay? Yeah, you can. So can you hear me? Yeah.
Yes, we can.
Yes. Okay. Okay. So so I hope it's recording now. And okay, so what we have is a system of equations, AX equals B. But if we look more closely, this is our A, this is our X, and this is B. And at any moment, we will be working with a certain basis. Okay, so it need not be contiguous, it need not be the first M columns. It is some M columns here, which will form the current basis. And with respect to that basis, you will have the corresponding variables here, which we denote by X sub B. And as we discussed last time, these X sub B will become the dependent variables, and the variables corresponding to this matrix, they will become the independent variables. Okay. And basically, we rearrange this equation so that these dependent variables show up here and the independent variables show up on the right, and this B gets suitably adjusted. Okay, so this B becomes P, the constant term, and these variables move from the left to the right. Okay, and that's what happens. And simultaneously, the objective function, which used to be here, we rewrite in terms of the independent variables. Okay, so the only thing that appears in the objective function here is the independent variables here, and there is the scalar constant. Okay, so if we just to make sure that we understand what is happening, so what should be this P? So if we know the B, what would we do? Okay, so we would take a part of AX to the right, and then we would have B times XB. Yeah, B times XB will remain on the left, but then we want only XB on the left, so we will multiply both sides by B inverse. So do you all agree that this P should be the matrix? What did I say? You take the matrix restricted to the basis columns, take its inverse, and multiply it by B. Is this okay? Yeah, this is how you will get this P. And what will be this Q? Well, once you took this part to the right, you would have so I'm going to write it down. If you have a question about that, please ask me. So I believe it should be AB inverse AN. Is that clear? Yeah.
Negative of that?
Sorry?
Will it be negative of this?
Negative of
Yes.
that. Thank you. Negative of that. Negative of that, because you would have taken AN to the right, and it would have, thank you. Yeah. And then the rest is, if you look at this objective function here, in that there is something that comes out of the basis variables. Those basis variable part, you will have to substitute in terms of the non-basic variables, which are the independent variables. And the coefficients
So the independent variables are the ones that are being set to 0.
That have been set to 0 at any moment of the
yes, while considering the current solution.
Correct. So the current situation is that these variables are these variables are set to 0. And if you were to stop Simplex right now, the current feasible solution would be that XB has been set to P. And under that setting, the current objective value would be Z0. Yeah. Okay. So let me just review what we do in Simplex method. We work with these tableaus, and I'm just going to assume that you all basically remember. Yeah. So how do we find the initial basic feasible solution? We set up an auxiliary linear program where we introduce these new slack variables, m of them, one for each equation. Okay. And we set, so we make sure that our right-hand side is non-negative. And then we can get a feasible solution in this case very easily by setting the value y to the right-hand side. And then we run our Simplex method, and we don't know whether it will stop. The main thing today is to show you an argument, a way of choosing the entering variable and leaving variable so that the Simplex method is guaranteed to stop. But for the moment, you assume that Simplex method will stop. So when it stops, either it finds a feasible solution for the original LP, in which case we proceed further, or it declares that the original LP is infeasible, in which case we just declare we are done. Okay, we don't have anything more to do. If we have found this feasible solution, solution, then we can start with that feasible solution, and we adjust the tableau. The top part will more or less be the same. We just drop the y variables, and at the bottom we would already have come to this sort of situation because the y variables would have all dropped out. And there might be a little bit of adjustment that needs to be done, but essentially you get this. Okay. Now, so right now we will be doing a Simplex loop on this. Yeah. So let us just recall what the Simplex loop looks like. If at this point, the coefficients of these variables which parameterize the current situation, yeah, if all those variables are less than or equal to 0, we actually have a guarantee that the linear program has reached its optimal value. The Simplex method has reached the optimal value because these xn's have to take non-negative values, and no assignment to these xn's would yield a value better than Z0. Okay, so that's where we are. But we may not be in that situation. There might be some coefficient in this R. So when I say R less than or equal to 0, I mean every component of R is less than or equal to 0. Otherwise, there might be a coefficient in R which is positive, strictly positive. So then there is scope for increasing this variable xn to improve your overall objective value. So we attempt to get hold of some xn. And how do we get hold of that xn? We use if there is only one xn for which the coefficient is positive, we don't have a choice. But if there are multiple xn's, we have to use some pivot rule to break the ties. We will see. Yeah. And we decide to make that a basic variable, that is, make that a dependent variable. So we go to the equation, we sort of imagine that we are going to slowly raise its value until one of the equations here becomes tight, and then we move this variable, yeah, the entering variable, to the left, and as a result, one variable corresponding to that equation, which was on the left, moves to the right. Okay, and we correspondingly adjust this so that the objective function is now expressed in terms of the new set of independent variables. And basically, there is one variable which has lost its status as an independent variable. So, but we have an equation here which has that variable on the left and other things on the right. We just take that equation and substitute here. We just plug it here and you get this. Or you might think of eliminating that variable by adding suitable multiples of that equation to the original objective function as written here. Okay, whichever way you want to think about it. So when we choose a particular variable to enter the basis, we have to decide which variable to leave, which variable should leave. And as I just said, we find the variable where
there is no choice for which variable leaves, right?
Well, there might be multiple coefficients here which are positive.
Oh, okay.
Yeah.
No, I mean, suppose you pick which variable you entered.
Yes.
Then, I mean, you will always try to give the maximum value such that.
Yeah, and it could be, and you're right, you will try to give the maximum value. Yeah, you try to get the maximum out of this iteration. But there might be multiple variables, multiple equations that simultaneously become tight. It's probably an unlikely case.
Right.
Yeah. So in that case, you will have choices.
Right.
Yeah. And again, exactly what you just said. So this is the value, basically the constant term and the coefficient of the variable which you are trying to move, their ratio determines how much you can increase this variable. Okay, the details are not very important. Yeah, it's much easier to do it by hand. Yeah, so and then but this quantity can be the same for many equations, multiple equations, and then we have a choice, and we might need to use use some pivot rule to determine which variable should leave the basis. And the same thing that happened here can happen at this stage. That is, sorry, no, not at this point. Yeah, no, sorry. This is a new thing that we might come to a stage where we found a variable which is very keen to enter the basis, but it can be increased arbitrarily without causing any difficulty to any of the equations. That is, no variable becomes negative. That is, its coefficient in all the rows is actually non-negative. So this variable can be increased without any other dependent variable having to be decreased. Okay, and that means we can increase the objective function indefinitely, and we declare the LP to be unbounded. Okay, so this is how, and after doing all this, we update the basis, which is clear. We always try to keep only the independent variables on the right. So are there any questions? This is the simplex method. The only thing we don't know is whether it is going to terminate. Now, why would it?
What is the pivot? Could you repeat what the pivot rule?
Yeah, so we don't know. We at the moment, simplex method has been kept as a scheme where by plugging in various pivoting rules, we will get various algorithms. Okay, so right now I will soon come to pivoting rules, but I hope this is clear that we right now don't know whether the simplex method will terminate, and why will it not terminate? Let us see. Okay, suppose at each step the objective value actually improves. Suppose this value actually improves at each step, then it has to terminate. Why? Because we only go through basic solutions. Okay, and once you determine the basis, the entire tableau is completely determined by the basis. Okay, so if this quantity is continuously increasing, that means we are never going to revisit an already visited basis. That means after a finite number of steps, n choose m or whatever, okay, you will have run out of bases to visit, and you have to stop either because you found the LP to be unbounded or because you reached an optimal solution. Okay, so the only problem is, only reason or the only thing we need to worry about is it possible for these iterations to go on and on and on without improving the objective function? And that means that whenever we identified a variable to increase, we could not increase it at all. That is, basically the component here was already 0. Yeah, because the moment you try to increase it even by the slightest, this one of the equations started squealing. Okay, so basically we are worried about those degenerate situations where variables, we are just not able to, improve the value of the objective function. Okay, and we need to deal with that. Now, for that reason and for other reasons of efficiency, one can ask, what sort of pivoting rules should we use? Okay, so let me just go over various rules that have been proposed. Some of them have advantages of efficiency, and basically from what I read in books, it has never been noticed, or it has been noticed only once, that the LP that arises from a natural problem actually cycles. Okay, I mean, it's a kind of a theoretical curiosity, and we will unfortunately spend some time on it. Okay, it's interesting in its own way, but in practice, usually hardly you never see cycling at all. Okay, so what I mean by cycling is that the system goes through one basis, another basis, another basis, and then returns to the original basis and keeps doing that all the time, not improving the objective function at all, and just changing, just like imagining that this is the dependent variable and this is an independent variable, and just playing around with independent and dependence without changing the current solution at all. Okay, so that rarely happens, but nevertheless, the original pivot rule that was proposed by Danzig, who actually invented this problem, and you should read the wiki entry for Danzig. I mean, it turns out that he solved 2 open problems in the area of statistics just through a misunderstanding. He somehow thought that the problems that were written on the board were homework, whereas actually the professor intended them to be open problems, and he just submitted them, and I think that became his PhD thesis also. Okay, so yeah, I plan to put some open problems in your homework. We'll see. Yeah. So, but anyway, it's a very inspiring story, and it just means that one just has to be brave. One should not be intimidated by the fact that some problems are open. So anyway, what was Danzig's rule? So Danzig's rule was that among the coefficients in the bottom line, so among the coefficients in the bottom line, choose the one that is the largest coefficient. That is, per unit increase in the variable, the objective function increases the most. Okay, so that is Danzig's rule. One could also worry that maybe this variable has a lot of improvement in the objective function per unit change, but somehow the constraints are such that we are hardly able to move this variable. So one could say that let us work and find out the variable for which the objective function is going to increase the most. Okay, that is, you will increase this variable until a point where some equation complains, and then you ask what was the resultant increase in the objective function because of that, and among the various candidates, choose that variable which improves it the most. Okay, so that is the largest increase rule. The rule that apparently is kind of the champion in practice is this steepest edge rule. So let me just maybe try and explain using a picture. What should I do? Let me just, where am I? Okay, so let me just draw a picture if I can. And yeah. Some such polytope is there, and you are at some somewhere a basic feasible solution. Yeah, I don't know how to draw polytopes. Yeah, but you are somewhere at one of the vertices. Yeah, and your, let us say your objective, that vector C is in this direction. That means from the current solution, yeah, from this current solution, we would like to move in this. Now, it may be that there are many ways of moving. There is one way of moving like this, and there is one way of moving like this. Yeah. Now, if you look at this, I mean, my lines are not quite parallel, but this thing is actually giving you a greater improvement than this. Okay. But this direction, it makes the best angle, yeah, with C. So it is most aligned to C. So among the various directions that are available here, don't pay attention to how much increase happens in the objective value. Move in the direction that makes the least angle with C. Yeah, it is the steepest. So I should actually have probably drawn this in a vertical direction so that C is upwards. Then we move in the direction which is steepest. Okay, in that sense. Yeah, move in the direction which is steepest. So if you look at the formula, what you do is you look at the new solution, subtract the old solution, and take its dot product with C. Yeah, and you normalize. So you take the unit vector in the direction of movement. So this amount is just a unit vector in the direction of movement, and then choose that variable so that the dot product of this unit vector, this part is the unit vector, its dot product with C is as high as possible, which is the same thing as saying that the angle is as small.
This is equivalent to which coefficient of C has the largest value, right? This will be simply the coordinate of C corresponding to that variable, right? This quantity that you wrote.
No, see, we are looking at the entire change in the vector itself, not per. So what, looking at the coefficient which has this is for the increase in the direction of that variable. Per unit increase in the direction of that variable, we are trying to find the best. Okay, here we are looking at the L2 distance, L2 length of the vector. Okay, the solution itself. So let me explain maybe. Yeah. Okay. So at any time when we so look at the largest coefficient strategy. The coefficient means one of the variables. Let us say we are trying to increase x7. We are asking for unit change in x7. What is the change in the objective value? That was the previous rule. Okay. Now we are saying for change in x7, this vector of ours, the current vector, is moving by some amount.
Okay. You want this angle to be minimized.
Yeah. So the amount of movement depends on where this vector is positioned. So yeah, if this original vector was like this, then the amount of movement is already in this direction. But if the original vector is like this, then yeah, we are trying to change. We are trying to measure the length of this vector. Yeah. Am I making sense? I'm not sure, but yeah. I'm also confused at the moment. So why is it different from that variable? No, sorry. Yeah. Anyway, there is a difference. Here we are looking at the entire vector, whereas in the largest increase rule here, we were only looking at that component. Yeah.
So suppose in the update step, you add T to the X width component, then the difference between the L2 norm of the difference is exactly T, right? and the numerator here will be coefficient of C into T. So these two should cancel out.
But this will not always be the same, this length. So what you normalize by may be different in the two cases, right?
X new, so X new is just X old plus
X old plus T times.
Okay, minus.
Right. So that depending on whether this variable is in the direction of the current X old or it is orthogonal to X old, there might be a difference in the denominator length here.
Yes.
Okay, so we are trying to take care of that. All right. Yeah, but maybe I'm not saying it very well. This is a different rule and it is apparently very fast and the others are relatively slow. Okay. Now, there are some other rules. There is this thing called Bland's rule, which I sort of praised last time and maybe sort of misled you into thinking that I'm going to present it today. So, but actually I will tell you about Bland's rule later, maybe next class. But let me just tell you the rule. The rule is the following, that you do the first, do the most systematic thing. That is, when first you choose which variable has to enter. Okay. So among the things that have positive coefficient in the objective function, that is the last row of the tableau, choose the first variable. And then try to increase. And while trying to increase, you might be in this rare situation where multiple equations become tight at the same time. Among them, choose the first equation. Not the first equation, the equation where the variable on the left-hand side has the smallest index. Okay. So always try to go for the smallest index of the variable. So what do I mean by that? Originally, the variables had names x1, x2, x3, x4, xn. Okay. So when you're trying to find a variable that enters the basis, tries to find the xi with I minimum, of course, with a coefficient which is positive. Okay. And similarly, when you are trying to find a variable that must leave the basis, you find that xj for which j is minimum. And and it becomes 0 at first. Yeah. Good. And then there is this randomized strategy here, where if you have multiple choices, you just choose one of them at random. Okay. And so the randomized strategy is used for proving that simplex method actually runs fast in some cases. I'll talk about it soon. Okay. But in practice, there are lots of tricks that one uses, but the steepest edge seems to outperform many others. Okay. So there is one more rule called the lexicographic rule, which also ensures that the simplex algorithm will terminate. Okay. So my plan today, so we have about an hour, but I'm hoping to use half the time for the lexicographic rule. Okay. So I would really request you to ask me questions if something is not clear. So the idea is this. Okay. The idea is that what happens is that when cycling happens, it is just because of some coincidence. That is, there were a certain number of equations that were supposed to be tight at some point. Yeah. Maybe if you are working currently in some d dimensions or m dimensions, there should have been m equations that are tight. But some of the non-negativity constraints also get satisfied with equality. Okay. Some more than, there are certain, what are they called? The independent variables which are 0, but some dependent variables are also 0. Okay. And that means more than the required number of hyperplanes are passing through a vertex. Okay. You don't have to understand this precisely. Yeah. So it is some sort of a degenerate case, something that has happened by coincidence. So the idea is to somehow perturb the RHS, right-hand side of the equations, so that this doesn't happen. And the perturbations are so small that in the end, their effect is not seen, and we can get rid of those perturbations. So I would like to do this presentation in a way where, this is from the book of Quatal, and this method of adding fake variables to represent perturbations is carried out in other areas of mathematics, maybe to resolve singularities and those things. Okay, so it's a good thing to know, but of course it is much more sophisticated in those areas. Here everything is linear, and so please ask me. So if you look at, so here's an example of a linear program, and if you run this linear program with this pivoting rule, okay, this is a rather strange pivoting rule. So when a variable needs to enter, you choose the first variable you choose the one with the largest index. You look from here, okay, meaning, you write the variables here in the order of their indices, and then you look for the largest variable, which is, but in this case, of course, there's only one. And when you want to leave, you choose the variable which has the smallest index. Okay, if you arrange the equations so that the smallest index appears on the top. So you look from the top, and here you look from the right. Okay, if you adopt this strategy for Simplex, then it turns out that this particular linear program, although it is bounded and everything, it will cycle. Okay, maybe in Quatal's book has the entire derivation. Maybe in 4 pivot steps or 5 pivot steps, it keeps coming back to the same basis. Okay, so we will take this as our running example and try to explain the lexicographic rule. So what is the lexicographic rule? So we want to perturb the right-hand side here. Okay, later on, all this perturbation will go away in our description of the algorithm. Okay, this is just the motivation for the lexicographic method. So imagine that the original right-hand side here, these values are all 0. So if you rearrange these equations so that all the variables go on the left, that is, all these parts are carried to the left, then what you will be left with on the right is some zeros and a 1. 0, 0, 1 is your current state. But what you do is, in the first equation, you artificially introduce epsilon 1. So let me do that. So you just say, I will write epsilon 1 here. And then here you write epsilon 2. And here you write. So you have perturbed these by epsilon 1, epsilon 2, epsilon 3. You should imagine that these epsilons are like this. Epsilon 1 is very big. Epsilon 2 is much smaller than epsilon 1. Epsilon 3 is even smaller, etc. Okay, good. So whenever you have distinct expressions like this, then we should be able to say which one is the smallest and then which one is the next. So these are all linear polynomials in epsilon. Now, why am I thinking of linear polynomials? So we will start working with this, and we will apply the simplex method to this. But we will treat this part as scalars. Okay, any expression which involves a constant or an epsilon is to be treated as a new scalar for us. It's a scalar. We will not explicitly write down the value for epsilon. We are not going to substitute epsilon equals 0.0001 or something like that. We will just imagine that it's a small number, and we will derive our algorithm. In the end, there will be no epsilons. Okay, let's just think about it like that. Okay, so now what happens is that at various simplex steps, you might be adding multiples of one row to the another. Adding multiples of some row to the objective function row. And as a result, these epsilons will not be neatly like this. Epsilon 1 is in the first equation, epsilon 2 is in the second equation, epsilon 3 is in the equation. They will be moving all over the place. They might even appear here. Okay, so we will still treat them as scalars. But remember that at one point, when we need to decide which variable leaves the basis, which variable leaves the basis, we need to find the equation, okay, where non-negativity is violated for the first time. At that time, we will be dividing this scalar, which is this expression like this, by the coefficient of the corresponding variable. And we would need to compare these values to determine which equation gets violated first. Okay, so for that reason, we need some way of comparing this. And as you can imagine, if I have told you this, then if you have only expressions like this, it's easy to say which one is the smallest and which one is the next smallest, etc. So can we just do a few? Which of the things that are here, which one do you think is the smallest?
Epsilon 1 coefficient is smallest.
Sorry, which one?
3 minus 4 epsilon 1 plus epsilon 2.
Do you think so? This one?
Epsilon 2 plus epsilon 3.
That's correct. So this one, yeah, good. Yeah. So epsilon 2 plus epsilon 3. Is this what someone else was saying something? But does everybody agree to this? Yeah. Okay. So basically, the constant term in this expression was 0. Yeah. All the others have some decent constant term, so they are all bigger than this. Okay. And then which one will be the next?
2 plus 10 epsilon.
Yeah. So, I'm sorry. Yeah. So 2 plus 10 epsilon 1. Yeah. So let me just scratch those two out. Yeah. So this is done. This is done. Yeah. And next, yeah. Sorry, is everybody thinking? So, yeah, epsilon 1 is the boss, right? It is bigger than everybody. So everybody has 3 as their constant term, I believe. And then there is this minus 4 epsilon 1 here and minus 4 epsilon 1. So far they are still equal. Then they both have epsilon 2 and plus epsilon 2. They are still equal. And this fellow has epsilon 3. This fellow doesn't have epsilon 3. I hope I'm looking. Yeah. So can someone? So which one is the smallest after this?
3 minus 4 epsilon 1 plus epsilon 2.
Yeah. So this one, is this what you mean? Yeah. Yeah. So I'm writing this. I will not go beyond this. So let me just write down. What did I do? 3 minus 4 epsilon 1, because epsilon 1 is so big, it drags 3 down the most. Yeah. And much more than this 3 minus epsilon 1, because this is 4 epsilon 1. And then there is plus epsilon 2, but epsilon 3 is non-zero. Yeah. So it has to be respected at the appropriate time. Okay, good. So you understand why this is called the lexicographic. So we are ordering it. So if we had just written down the coefficient expressions and read it like a dictionary from, I mean, as we read words in the dictionary from left to right, if you were to sort this and place it in a dictionary, the one that appears earlier is to be considered smaller than the one that appears later. Is this clear? Yeah. Okay. So what have I told you? I have told you how to start. So the moment you notice degeneracy, what we will do is we will introduce these fake scalars here and simultaneously tune our minds so that we know how to compare distinct scalars. Scalars are now going to be expressions like this. Okay. And then let us see what happens. So if you perform one, so now 10. Yeah. So let us do one step. So this is 10x1. We want to increase x1. Okay. So can someone tell me how much can I increase x1 by? So if I increase x1, this equation is going to protest when I increase x1 to 1 plus epsilon 3. If I change x1 to 1 plus epsilon 3, this equation will become tight. Whereas this equation will become tight when x1 becomes what value?
Epsilon 2.
There is a 0.
2 epsilon 2.
2 epsilon 2. And this equation will become tight when x1 becomes?
2 epsilon 1.
2 epsilon 1. So which equation becomes the tightest first? Tight first?
2 epsilon 2.
Yeah, this equation. So who is going to leave the basis?
X6 will come in the basis.
X6 will
leave the basis.
X6 will X1. Yeah, somebody had a question. Was someone saying something? Someone else? Okay.
No.
So everybody agrees. Yeah, everybody agrees that once we have these things here, the ambiguity has been removed, at least for now. Okay, because we put distinct values there, so the ambiguity has been removed, and we choose the one where raising x1 causes the problem. So how much are we going to change x1 to? We are now going to change x1 to 2 epsilon 2. Okay, and we are going to eliminate x1. Okay, so we are going to eliminate x1, meaning we are going to take this equation and subtract it from the first equation so that x1 goes away. So what we should see there is something like epsilon minus epsilon 2. Sorry, why did I see 2 epsilon 2? Oh, sorry, I have reordered the equation also. Yeah, so the x5, in the expression for x5, we are going to eliminate this x1. So we are going to subtract the second equation from the first. So this will go away. Here you will see epsilon 1 minus epsilon 2. And this particular x6 would come as minus x6 in the equation for x5. Okay, so if you see that, I don't know if I should close this. So can you see that in x5, epsilon 1, I moved x5 down so that my variables are all in the right order. So epsilon 1 minus epsilon 2, trust me, these were done right, but the x6 comes out here. Okay, one thing you should remember, and I would like you to think about, see the coefficient of x5 and epsilon 1, yeah, they are paired in the sense that suppose I moved all the variables to the right and called this 0, 0, 0, yeah, moved all the variables to the right. The coefficient of x5 and coefficient of epsilon 1 are negatives of each other. Okay, the coefficient of x5 will become 1, epsilon 1 will be 1, and x5 will become minus x5 here, right? Yeah, if I move this. So epsilon 1 and x5 have coefficients that add up to 0, or they are negatives of each other. Okay, and this will continue always because we are just going to add multiples of one equation to the other in this entire simplex process. So you should imagine that wherever x5 is there in that equation or in that objective function, epsilon 1 will also be there, and they will have opposite coefficients. Okay, so if you did that, that is, you eliminated x1 from the right hand side by, so if you wanted to eliminate this one, you would probably multiply this equation by 2 and add it to this equation so that x1 goes away. Okay, and do various things as we are used to in simplex, and trust me, you get this. But let us just check the what did we know initially? That x5 and epsilon 1, they have the same they must have the same coefficient. Let us just empirically test that they must have negative coefficient. Here they do. Yeah, x5, if it were moved here, would have got a -1 that we just checked earlier. Epsilon 2 was tied to x6. Yeah, and here x6 has +1 as a coefficient, epsilon 2 has a minus, and somehow something went wrong. Maybe my theory is all gone crazy. What happened to epsilon? Sorry, epsilon 2 and
how did 20 epsilon 2 come?
Because we have to eliminate x1 from the right hand side here. Yeah, so yeah, but in x6, sorry, what were we doing? The equation for x6, there was an epsilon 2 already here, and x1, yeah, that's right. Sorry, can someone help me? What happened to this? My first, where did I get this equation from?
Yeah, it should have minus 2x6.
It should have minus
Which is missing.
2x6.
Yeah.
Yeah. Yeah, I would have multiplied this equation by 2 and moved this x6 to the right, right? Yeah. So
Yeah.
good. I had that sanity check done. So in which equation? This equation I should have minus 2x6. Is this what you're saying? Yeah. Okay.
Yeah.
Thank you. Okay. So.
Oh no, Jaykumar, you wrote a minus 2x2 there. That should have been minus 2x6. That's all.
This minus 2x2 I wrote twice.
Right.
Yeah. I'm sorry. I'm so bad at this. What do we do?
Yeah, exactly. That should be x6.
Okay. Okay, good. But remember, and this, I mean, it's much easier to kind of talk in the air about this. x5 and epsilon1, they are going together always as we are doing simplex method. So their coefficients must add up to 0. Yeah, if properly thought about. Place them on the same side and compare. Similarly, x6 and epsilon2 and x7 and epsilon3. Okay, good. So now we are in this situation, and let us see which variable should enter the basis. Sorry, I hope everybody understood. I've not done every step of this tableau, but
x5.
x5. Why? No, I'm talking about this one. This tableau. So if you look at the objective function, which variable looks like it is going to improve the objective function?
x3.
Oh, sorry, maybe you read this as x5.
X3.
Yeah, it's x3. Yeah, sorry. Yeah.
There is only one choice here, actually.
There is only one choice here. That's not the problem. But now when you make this choice, if you try to increase x3, okay, let us see. This is the only place where it appears as negative. These two, there is no, we can increase x3 arbitrarily and nothing will go wrong. Okay. But here, if we increase x3, at some point, this is going to start complaining. But yeah, so we just exchange x3 and x7. Yeah. And I don't know what I've been doing, but I don't know why I have a 2x7 here. It's all a mess. Yeah, most probably this shouldn't be there, but I wish, I mean, even copying I can't do properly. But anyway, so we eliminate x3 from all the equations. Yeah. So, and so basically we multiply this last equation by 2 and add it to this to eliminate this. If we multiply this by 2 and add it to this, you see, I hope what is written here is correct. Epsilon 2, when I multiply by 2, it becomes minus 4 epsilon 2. There was already an epsilon 2. So it becomes minus 5 epsilon 2. Okay, so at least one thing was right. And you get something like this. Yeah. And sorry. And similarly, when you try to eliminate x3 from this, well, you will add this equation to this one, and with the x7 on the right side, etc. So this x3 will cancel, and you will have some other expression, and this epsilon 2's coefficient from 20 epsilon 2, and this minus 2 epsilon 2 will interact and become 18 epsilon 2. Never mind, we will get something like this. And at this stage, we notice that all the coefficients are, none of them is positive. Yeah. So we have reached the optimum solution. Okay. So in the previous, if we had run this original tableau with these rules, it would have cycled, but now it is not cycling, it has come to rest. Yeah. And the theorem is that if you apply this method, yeah, with these fake scalars, then the simplex method will not revisit a previously visited basis. Okay, and it will terminate. Yeah, and we are done. Okay, and after you have terminated, you just set all the epsilons to 0, and it looks like an honest tableau. Yeah, and there's no problem. Okay, so, but we need to show a few things. I mean, how do we know that when simplex is applied to this situation, yeah, this situation where we have put in constants, we will not again get into degenerate situation. Yeah. Okay. So the strategy will be the following. We will argue that at every stage of simplex, the right-hand side here, the scalars, now by scalars, I mean these green entries. These green entries. These scalars will be non-zero in every row. Okay. In the original simplex, when we were dealing with constants that were inherited from the original LP, there could be zeros. I mean, you see, there were zeros here. Yeah, so there were these zeros, but that is, we inserted epsilon 1, epsilon 2, epsilon 3 to avoid those two zeros and maybe for some reason here. But now onwards, the claim is that the scalars that will appear here will always be non-zero. Non-zero as polynomials. Yeah, that I'm not saying that constant term will be non-zero. If you look at the entire polynomial in epsilon 2, it's a linear polynomial. Yeah, something times epsilon 1, something times epsilon 2, etc. That quantity will always be non-zero. So what? So what? Well, what happens is, because of that, at every step, yeah, when you try to increase the variable, you will be able to increase the variable at least a little bit. When are you not able to? This I should have said before. When are you not able to increase a variable? When the scalar part of that corresponding equation is 0. But if you have arranged that the scalar part of that corresponding equation is not going to be 0, then you know that in every step of simplex, you will be able to increase the objective function, which means this quantity here is going to continuously change with each simplex. But you can again imagine that this quantity is completely determined by the basis. Once you tell me the basis with these scalar values, you can do the same linear algebra, the first thing that we did today, A, B inverse and multiply, etc. Then once you fix the basis, even in this extended setting with these fake scalars, the tableau is completely determined by the basis. And since this quantity is continuously increasing, we can say that we will not revisit the same basis again, hence simplex terminates. Is that clear? This is going to be the line of argument. The only thing we need to show is that at every stage, every equation here in our intermediate tableau will have non-zero entries, non-zero scalars in this extended definition of scalar. Sorry, I somehow sense that I'm not being very clear. So if somebody can ask something.
So you have eliminated degeneracy, is it?
I have eliminated degeneracy because I have declared certain degeneracies to be non-degeneracies, because I will be able to compare these numbers. So I will know. So there are two things. I'll show that every stage these scalars are non-zero and they're actually distinct non-zero scalars. Okay, so in fact, there will be a unique minimum among them. Yeah. So if you, we did some practice with some polynomials, but you can imagine that if you have distinct polynomials in lexicographic order, in the dictionary order, there will be a unique one. Okay. So we will have to argue that, but we have eliminated degeneracy.
Thanks.
So at every step, the variable which has a positive coefficient will increase. It may be just a nominal increase in terms of the epsilons, but it will increase. Okay. And also, the quantities that will appear here will always be non-negative. They will actually be positive, because initially they were positive, right? When we first introduced the epsilon, all these quantities are positive. What if at some point minus 2 epsilon 2, etc. comes? Okay, then we will be in trouble, because when we recompute the value of this x2, increase x2, actually it will amount to decreasing x2 because if this quantity is negative. But no, we will always ensure that all the quantities here are actually positive. And yeah, it will actually be non-negative. And that is because of the same reason. We are choosing that value of, x1, which makes the first equation complain. So after this readjustment, other equations are not complaining. That means their values are, they are definitely not negative. Okay, we will actually prove that they are positive, but they are not going to become negative. So don't worry that at any point something is going to become negative. And so since these are always going to be positive quantities, the objective function is always going to increase, and we are not going to revisit a basis. Okay, I'm saying the same thing again many times. Okay, good. So now this is where we were, and everything rests on this. At the end of each pivot step, the scalar term, and by scalar term, I mean the term which looks like this in that equation, in each row is non-zero. Okay, by each row, I mean each row of the equation part. I didn't mean the, yeah. So
in this case, it could still be the case that when you are deciding which variable comes in the basis, there might be a tie there.
that's right. So we have, sorry, I should have said that. So it may be that the entering variable, there are multiple choices. Okay, in this case, of course, there was only x3, but there might be multiple choices for the entering variable. Choose anything. So this pivot rule does not specify which variable to choose, and this pivot rule guarantees termination no matter which one you choose. So let us, for definiteness, say that we will choose the first one. Okay.
Okay. As long as the value increases, it does not matter.
Yeah, and because we have ensured that the right-hand sides have non-zero positive scalars, we are always improving the objective function. Okay, and so the process will terminate, provided we can prove this claim. Okay, now let me just, this is, it's a very nice linear algebra argument. You probably already see it. Okay, so what is happening? So I'm going to prove this claim. Is the claim clear? Please ask. Yeah. Claim says that as simplex method proceeds, after having embedded epsilon1, epsilon2, epsilon3, various things happen, but you will not zero out that expression in the front, the scalar in the front in any. Okay, the constant b part, things that came from b might cancel, things that came from epsilon will not cancel. And the reason is this. So initially, what was it? Initially, the scalars looked like this. Yeah, in the first row you had b1 plus epsilon1, in the second row you had b2 plus epsilon2, bm plus epsilon1, m, bm plus epsilon m. This is just when we started. Okay, and let me write this as this. So this is 0 here, and if I take this matrix and multiply it by this vector, yes, then I will get this. Yeah, b1 times 1 epsilon 1. Yeah? So you understand, this is a little identity matrix here, m cross m, and there is an extra column here, but corresponding to that column, this vector has 1. This has these abstract values epsilon 1, epsilon 2, epsilon n. Okay. Now, what are we doing to these scalars? In each step, we are taking one equation and multiplying. Either we are scaling the equation. When we want to introduce some variable, we take that coefficient and divide this entire equation by that coefficient, so let us see, when did we do it? So here, x3, okay? So maybe we divided, okay, in this case, it was -1. You know, there was that 0.5 or something at some point. Where was it? 10x1. Yeah, so we would have divided the entire equation by maybe 0.5 or -0.5 and taken x1 to that side. Yeah, so we divide by 0.5 and take. So at each step of the simplex method, what are we doing? We are, we are multiplying some equation by a scalar and then adding it or subtracting it from another equation. This is what we are doing. So what is happening to this? if you look at it in terms of this, in this expression, we are continuously, each time, whatever we do in that pivot step corresponds to an invertible operation. We are adding one row to another, scaling one of the rows. If you scale one of the rows, it corresponds to multiplying by, I don't know, 1, 1, 1, the alpha scalar there, like this. Or if you add one multiple of one row to another, anyway, you have some scalars. So you know that these are elementary matrices from your linear algebra. So at each step, you are performing an elementary step to the whole system of equations. But let us focus. Let us focus on the first m+1 columns where the scalars reside. And there, it looks like this. You started off like this, and each time you are multiplying this matrix by some elementary matrix E. And as a result, you get a new set of scalars. Yeah? So you understand? The scalar terms are subsequently modified when we scale an equation or add a multiple of one equation to another. Okay. These operations correspond to multiplying the vector of scalars, the vector of scalars, yeah, by a non-singular matrix. This elementary matrix I have called B. Okay. At each step, you are multiplying it with this matrix. Yes, I shouldn't have used the letter B. Should I call it? I'll mess it up. Oh, should I? So this I should call, let's say, the elementary matrix E. Yeah. And then, sorry, what am I doing? Yeah, so there is the matrix E. Is that clear? So if there is a question about this, please ask me. We are just at the end. Okay. So if you ask, what does the expression look at some later stage? Yeah. So you started off with this, and at any stage, you would have multiplied several elementary matrices. So it's a non-singular matrix here, and you have multiplied this. Let us multiply. Let us multiply this with this. So the first column here becomes this column of original vectors times this elementary matrix. And this part of the matrix, this E comes and sits here. Okay. So E is some matrix. And what do we know about E? E is non-singular. Now, if I multiply this, what will I get? These E1 to EM will get multiplied by the first row here. And there is no cancellation. E1, E2, EM have separate identities. There is no, they are independent random, they are different random variables, independent in the linear algebra sense. They cannot cancel each other. So what will I get as the first scalar here? First scalar will be the first row of this multiplied by this. Now the first row of this could well have had a 0 here. I don't know. But all these coefficients will get multiplied by this. So I will get some expression here and some expression here. Now, basically, the expression that I get in the end will be just the rows of E. But E is a non-singular matrix. So all its rows are linearly independent. This part is M cross M. All its rows are linearly independent. In particular, they are all non-zero. That's it. Yeah. Since the rows of B are linearly independent, the scalars that appear on the right-hand side of the tableau are linearly independent polynomials in E1 to En. Okay. And so they have to be non-zero. You want me to say this again? Imagine what Simplex does to this part. It is repeatedly applying a non.
So this is multiplying each constant part by an elementary matrix at each step, right?
By elementary matrix at each step, and those elementary matrices can all be combined, and when we multiply them, they become a non-singular matrix.
Well, okay, but in that case, you know that the whole vector will not become 0, right? But then how do you ensure a single coordinate does not become 0?
No. These are look at what happens in the end. So here was this vector of these abstract variables, and you have multiplied it with this matrix, right?
Yes.
So the coefficients that they will acquire will be precisely the same coefficients that E had there. whatever
Okay.
whatever were the values of E here, there was a certain scalar E11, E12, E1M. Yeah. So the coefficient of epsilon 1 will become E11, the coefficient of epsilon 2 will become E12, and coefficient of epsilon M will become E1M, and that is in the first scalar after this pivot step. Okay. Now the coefficient of the second scalar here will come from the second row of this, will be precisely these values, but we know that these are non-zero. Each of those rows is non-zero. These
Yes.
rows are, is this clear? Sorry, I'm just, yeah,
Yes.
I'm saying it so many times that now I'm not convinced, but anyway, it's okay, I hope. Yeah, the point is that these are all linearly independent rows. They cannot become zero. Yeah, that's it. Okay, so now suddenly we treat these epsilon i's as somehow abstract basis vectors in some vector space. Yeah, so we are working in the vector space of polynomials and in m variables. Yeah, go
okay,
ahead.
right.
Please
So
say.
you're saying treat this constant terms as a matrix, and then the simplex operations is simply left multiplication by an elementary matrix.
Perfect. Yes.
And I mean, and what we want to show is that such operations do not make one row to zero.
Yes.
And that is because, well, Gaussian elimination works.
Or there was an identity matrix. When you multiply the identity matrix by the matrix, you get the same matrix.
It or simply it's, I mean, it's a subset of the steps you do in Gaussian elimination. So.
Okay, fine. Yeah, whichever way you want to think about it.
Right,
in the end, you get the matrix E here, and this E will ensure that each of these epsilon m's, yeah,
all these rows are linearly independent.
Yeah, these epsilon i's are not going to cancel each other, yeah, because we are going to treat them as abstract values. Is that clear? Okay, good. So slightly behind, but don't worry. Now, this means that we are going to do some funny simplex, where in addition to our usual favorite real numbers, there will be these epsilon i's, etc. They are symbolic for a computer science. I mean, even numbers don't exist. Everything is a symbol. So we will have to play around with these symbols. However, I would like to return to my observation, which I had messed up. The point is, in the end, in order to determine what we are doing, we just need to know the coefficients of these epsilon i's. Is that correct? I mean, at any step, to determine which variable enters, the variables coefficients here are true, honest to God scalars, old-fashioned real scalars. The only time we get these fake scalars are here, and we need to compare them. In particular, we need to keep track of them to find out what they are. But in every row, the coefficient of epsilon 1 is the same thing as x5. They are paired or something I said before. Okay, so actually we don't need the epsilon i's. Yeah, so when you run this lexicographic method, there is no harm in running this lexicographic method symbolically, but there is a certain redundancy. We will just look up. So when we want epsilon 1's coefficient, we say that epsilon 1 was introduced for x5. We look at the coefficient of x5 in that equation, and whatever it is, we take its negative. Okay, so x5's coefficient in this equation is -1 if it was put here. So epsilon 1's coefficient is 1. Epsilon 2's coefficient depends on whatever is x6. So in the second equation, x6 was +1. So epsilon 2's coefficient is -1. So actually this part is not needed. We could have just used these to figure out which one is what are the scalars there. And we can implement our lexicographic first rule by using these coefficients themselves. Okay, I will leave it at that. Exact writing of code, whether something should be plus, something should be minus, and in which order these things have to be examined, all that is just a matter of computer science detail. But this is the heart of the matter. Okay, so if you want to work with these epsilon i's explicitly there, that's also fine. It will just be a redundancy. This will be redundant. Any questions? So if you have this claim, the objective function increases at every step as a polynomial. Yeah, it may not be a real increase. It may still be zero. Once you set the epsilons to zero, the increase will vanish. Okay, but nominally there is an increase, and we leverage that nominal increase and the fact that in the lexicographic system, every two numbers are comparable. Yeah, I mean there's. So please ask if there's. Okay.
So
Yeah.
don't we need non-negativity of? So we proved that these are non-zero, right?
I said non-zero. This claim has only proved non-zero,
Yeah.
but how? So to show that they are non-negative, we say the same thing that we said for the original simplex. Whenever we do a pivot step, we substitute for some variable. I forget where is our variable. At this point, I think x3 is going to be substituted, right?
Yeah.
For x3, we are going to substitute from one of the equations. But we will be choosing the equations in such a way, choosing that equation in such a way that it is the first equation to turn negative. In particular, at that value of the substitution, the other scalars will change but remain positive.
Yeah. Okay.
Yeah. So we are not using this linear algebra method, linear algebra argument for positivity. For positivity, we are using our old common sense from simplex method, or rather non-negativity. We are certain that all these quantities will be non-negative because we are very careful in choosing the value of the entering variable. The value of the entering variable is chosen in terms of the polynomial. Yeah? We treat that polynomial as a scalar. Yeah? But notice that we never, those funny scalars don't appear as coefficients. These coefficients always stay, honest to God, real numbers. Okay? They come in here and here. Yeah? Etc. Okay, please ask another question.
Is it in general true that for any vertex of the polytop, these coefficients will be non-zero, or just the ones visited by the simplex?
Yeah, good question. Yeah, so maybe we should spend some time. So there are many ways. So yeah, if you have time, you should read Kotal also. The point is that we could have done this substitution of epsilon1, epsilon2, epsilon3 to the very first simplex. Yeah, so after we run the auxiliary LP, we got an initial basic feasible solution. Just because we are paranoid about degeneracy, we could have added epsilon1, epsilon2, epsilon3 there. Yeah, and we could then onwards continue. And your question is, even then, yeah, whether you encounter degeneracy or you don't encounter degeneracy, the scalars in all the rows will remain positive polynomials of epsilon1 to epsilon n. That is one strategy. And as far as theoretically showing that simplex terminates, that is perfect. In practical situations where lexicographic method needs to be used, yeah, what one might do is that as soon as one encounters degeneracy, we hurriedly introduce the epsilon1, epsilon2, epsilon m at that point, and we continue. The moment the degeneracy ends, that is, we make a true increase in the objective function, not a fake increase in the objective function. Okay, we say, we are out of that degeneracy, we throw away the epsilon m and run the old simplex until we meet degeneracy again. Okay, and then introduce the epsilons, try to get rid of the degeneracy and make a move. Okay, that is also a perhaps more efficient way of doing this, or even more efficient. Whenever we have degeneracy, we don't in a hurry try to introduce epsilon. We wait for some 20 iterations. And we see that the degeneracy is persisting for 20 iterations. We suspect that there is probably going to be a cycle. At that point, we introduce epsilon1 to epsilon m. And we know that once we have epsilon1 to epsilon m, it is some sort of, what should I say? Medicine, which will get you out of that disease. And then you again proceed until you meet the degeneracy again. Okay. Yeah. So we don't keep the medicine all the time with us. Okay. Yeah. We just use it when we hit degeneracy. That's also valid. Yeah. Okay.
Does it matter? Sorry, a question.
Please, please.
Yeah. Does it matter where the epsilon1 and epsilon2 these are going? Like in here, it is going to x5.
No, it doesn't matter. Yeah. So we could have called. So I actually, for this presentation, it would have been nice if I had called this epsilon5, epsilon6, and epsilon7 so that we could keep track of it nicely. It doesn't matter. Okay. And you could have put epsilon1 here, epsilon2 here, and epsilon3 here, and continue to declare that epsilon1 is bigger than epsilon2, etc. They just should be distinct abstract quantities with an understanding that one of them dominates the other in this way.
So, Jacob, the upper bound of 1, was it a function of x7 having a 1 there, or was it, if it was some much smaller quantity instead of 1 there, would you have?
Yeah, I mean, the final, if right in the beginning, the objective function that we get, I don't know, I made you write Z0 as CB transpose P, right? So this P, which is the original P that appears here, that determines this value. Yeah. Is that what you asked? Yeah.
No. So you had upper bound of 1 on all the epsilons?
Oh, why did I have an upper bound of 1 on the epsilon? Sorry,
yes,
that's what it, no. That is just because, actually, maybe I should, because when I have an expression, this is just for thinking purposes, when I have an expression when an epsilon and a constant both need to be compared, yeah, or like this, yeah, 2 plus 10 epsilon. How do I know that 2 plus 10 epsilon is less than 3?
Well, okay, so basically epsilon1 is smaller of 1.
Yeah, it is so small that even multiplying by, but I think this is the wrong way of thinking about it. Let us just say that these are abstract numbers. Scalar dominates epsilon1 dominates epsilon2, etc. Actually, in the standard treatment of lexicographic method, they would call this epsilon squared, epsilon cubed, etc. They are powers of epsilon, so that they are like Srijato said, they are like little o of each other. Okay. Yeah, so that's why this is 1, much smaller than 1, so that any multiple of epsilon1 will never be able to make this 2 jump over 3 or any other constant scalar that appears ever.
Sure. I just wondered if x7 was 1 plus 1 minus x1. Was this 1, instead of, there was a 1 over 1 million there, would you have put an upper bound of 1 over 1 million? That's it.
That I have, actually, this is, I have put a much greater than. So my epsilon1
right.
is less than 1 over million already. Yeah.
Sure.
Yeah. That's right. Yeah. So that is one way. I mean, if you're really like a numerical person, you will actually set these epsilon i's to some value which you will determine by looking at the coefficients in your LP, and you will run the LP completely like without any worries. That is also done. Okay. That is, let us not mess around with all this lexicographic, etc. Right in the beginning, find a reasonable value for epsilon1, epsilon2, epsilon3. Yeah. So that every expression that will ever appear in our LP will always be decent, and the right comparisons will take place. And then we do that. But there you are always worried. Did you do the computation right? If you keep them abstract, then you can just apply the lexicographic rule. If you did that, then you wouldn't have to do the lexicographic rule. It would be just some perturbation method. Yeah. Okay. So let me just, I was planning to reach duality today, but let me just take the remaining 5 minutes to tell you about the efficiency of the simplex method, and then we will stop. Yeah. And we will do duality next time. Okay. So this is just some general guess, and there is no technical depth here. So in practice, simplex requires only a small number of iterations. So even it is people believe it just needs linear number of iterations. Yeah. So this is what one encounters. But for a long time, it was even believed that simplex will always stop no matter what you did in a linear number of iterations. But then there are examples, these are called the Clementi examples, where actually you have n equations and n variables, and those equations have been set so badly that if you use the Danzig rule, which is the largest coefficient, largest coefficient in the objective function, that rule, then you would need about 2 to the n steps. Simplex would take 2 to the n steps. And similar examples have been constructed for other rules. There is a particular randomized strategy where there is no such rule. In fact, one can show that if you use the randomized strategy for any LP with n equations and n variables, then it will stop in 2 to the square root n steps. This used to be 2 to the n, so it does better than this. And at the moment, we don't know of any theoretical result which would show that simplex, in the worst case, would do better than this. So here, the input is worst case. You give me any input, but the simplex will be run with this randomized strategy. And what is the randomized strategy? First, you order the variables. So there are n variables. You can order them in n factorial ways. Pick one of the orderings, and then apply Bland's rule. That is, always choose the first variable with respect to that order. And then you can prove that it would take this. I have not looked at this paper. Apparently, two groups proved this result simultaneously. Now, if you remember, our course has a presentation component. So if you are interested, if you like probability, probabilistic analysis, probability and geometry, which is a wonderful area, this might be a good introduction for you to this area. So please consider, I will put up the paper somewhere, Kavita and I will figure this out. And this, I hope, will be one of the options for you to choose from. On the other hand, you could just say that what happens to LPs on average. Like suppose I pick up an LP at random. Okay. Now you'll need to define what distribution the LP is coming from. But it is known that for certain probability distributions on LPs, certain ways of choosing the coefficients and the sparsity and all that, LP actually runs in expected polynomial time. So but you know, this business of average case analysis is always tricky because you might do average, you might test your LP package against average with respect to some distribution, then you bring it to your company, and the kind of LPs that arise in your company are completely different. Okay. And but still, it is good to know that at least there are reasonable distributions on the coefficients where LP can be shown to stop in expected time. This is an old result from the 80s. Yeah. This is relatively newer. Yeah. But sort of the more spectacular and what should I say, celebrated result is the result of Stillman and Teng, which says that if you take any LP, and you perturb it locally using some noise that is on each variable of the LP. So you modify the LP. So you give me the LP, the worst LP that you can. I will just perturb them randomly. Okay, I won't like carefully change the coefficients by looking at them. Just randomly add Gaussian noise to each of the variables or the LP in a certain way. And then I will run simplex. Okay, according to some rule, some pivot rule, which is different from everything else. And then it can be shown that no matter which LP you give, with that pivot rule, you would the simplex method would terminate in expected polynomial time. Okay, so that is called smoothed analysis, and this is somewhat technical and difficult work, which is celebrated. It has won many awards. And so after this, I was planning to do duality and actually show the strong duality theorem as a consequence of simplex. That is, so many of you know that the dual program when you are a maximization, when the primal is maximal, the dual forms an upper bound for the primal. And actually, if both are feasible, there is an equality here. Yeah. And proving this equality is called the strong duality theorem. Yeah. So it turns out that we know that when we terminate in simplex, the coefficients in the last row all become, none of them is positive. From that fact, strong duality follows. Okay. And I was hoping to do that, but I've run out of time. So I will start next time with introducing duality in this way. That is, from simplex, we get another, the dual linear program. Dual linear program we get anyway. From the fact that simplex stops in a certain way, we are able to extract a solution for the dual program. Okay, and that proves strong duality. So it's okay if what I just said didn't make sense. We will discuss this next time. But the homework is due in a week. Please stop by or send me email if something is not clear or you're struggling with them. Okay. So I'll wait for your questions, and then you can leave if you have. Yeah. Thank you very much. Any questions?
I have one question. Like,
yeah, sorry.
Yeah, Ashman. Yeah, question.
Yeah, please go ahead.
Yeah. When we are taking that epsilon1, epsilon2, those things, and we're saying that there is a polynomial over that, like first time I was not understanding why it is like called polynomial over epsilon1. Then, but the thing that you said that epsilon, then epsilon square and that power.
No, these are, I mean, sorry, this is a polynomial in two variables. Just happens that the exponents never go above 1. These are all linear polynomials.
Okay.
Okay. Yeah. I know. I mean, these are kind of what should I say? Yeah, very poor man's polynomials. Yeah, polynomials where the variables degree don't. Yeah. So I don't know what I should call them. I should call them linear forms or affine forms in the variables epsilon1 to epsilon m or something.
Yeah,
But
okay, I understood. But that the first, what you said in the second thing, that epsilon, then epsilon square, that actually like it was like much better for.
Yeah, but
the power is like changing in the polynomial.
Yeah, so you should, but somehow, yeah, it's okay. Yeah, but then treating them, see in the final argument that we make here, treating them as independent variables becomes a little tricky. So it is better to keep them completely independent to think about it like this. But even with epsilon squared, if you say that the monomials epsilon1, epsilon2, epsilon3, etc. are linearly independent monomials, okay, which is how we think about them in algebra, then we are sane. So maybe if you want to think about it like that, that's fine. The only advantage here also is that I can say that epsilon i's value, the coefficient, is tied to the coefficient of some other variable. There I will have to say epsilon1 to the power something is tied to something else. They're the same, doesn't matter. All right, if so if you have any questions, please ask. Okay, thank you.